Good morning all. In this class we will be discussing X-ray diffraction techniques and determination of the crystallite size and the crystallite structure using these X-ray diffraction techniques. In the previous classes we have discussed the various classification of engineering materials and classification of materials based upon the crystal system. Okay, the lattice systems, how the materials are getting classified. For example, the cubic classification, we have simple cubic materials, body centered cubic material, face centered cubic materials having different crystal systems, and also these materials exhibiting different types of properties based upon its structure property correlations. So when we are considering the material science or the materials engineering, one very important factor is the material characterization techniques. So how we will determine different features of this particular material. One very important characterization technique is the microscopic techniques or the microscopic characterization, where we will be using the structure of the materials up to the grain size, the grain structure and the grain size measurement. All those things will be considering under the microscopic characterization. And in microscopic characterization we cannot go in deep into the crystal structure or the atomic arrangement. So X-ray diffraction technique is one such techniques in which we can find the atomic arrangements inside the material, or we can see the crystal structure determination. While discussing about the atomic structure and discussing about the atomic planes, we know every materials are if we are considering a polycrystalline material, it will be consisting of number of atoms which will be oriented in particular directions. So inside a grain we will be having atoms arranged in one particular directions, and when we are going to the another grains we will be having atoms arranged in a different direction. So if we are considering a polycrystalline material itself, we will be having different groups of atoms periodically arranged in different planes. So it is very important to know these planes, to determine these planes in which the atoms are arranged. So we have to know the crystal structure of the materials, we have to determine the different planes from which these atoms are arranged. So X-ray diffraction techniques is one such techniques which can be used to determine the crystal structure, the phase structure of the material, crystallite size or the grain size of the material, and the reflections from the different planes. Okay. So before going in deep into the X-ray diffraction techniques, first we have to know some basic principles regarding these XRD or the X-rays which are emitted in these X-ray diffraction techniques. So in these particular characterization techniques, the incoming rays or the parent rays which we are using for the characterization, it is an X-ray which is emitted from a cathode tubes, a copper cathode tube. These X-rays are actually electromagnetic radiations or electromagnetic rays which are having a particular characteristics of a wave nature. So it will be having a wave-like nature, and so it will be exhibiting certain features which normally shown by the waves. So it will be having a wavelength, and these X-rays are having very short wavelength, the short wavelength of the order of the interatomic spacing between the atoms. So why that is one reason why we are using X-rays for these particular characterization techniques to determine the crystallite structure. The reason is the wavelength of these X-rays are having very close similarities or very close range with the atomic size or the interatomic spacing. Okay, so in XRD techniques we will be using X-ray as the main source. So we will be having an X-ray which is an electromagnetic radiation. It will be having a particular wavelength which is a shorter wavelength. So next is two important features of the waves, which we will call it as interference of the waves. Okay, we have two types of interference. One is the constructive interference, another one is the destructive interference. So if we are considering two waves, as in the figure we are having two waves. If we are considering the extreme left side, we will be having two waves which are having a similarity in its phase. So both are in, we can say both are in phase. The wave 1 and wave 2 are in phase. Okay. So next they will be subjected to a particular obstruction or a particular hindrance in its path. So we can say the wave 1 is undergone an obstruction in its movement by a particular object. For example, it can be an atom. And the wave 2 is also subjected to an obstruction or a hindrance by another atom, not the same atoms. So we can say the both waves are having an hindrance in its path. So after that, when it strikes an atom or an obstruction, it will tends to get scattered. So the wave 1 gets scattered from its path, and wave 2 also it is getting scattered. So after this scattering process in the wave 1 and the wave 2, if the waves are again in same phase, if the waves are again following the same phase, we can say it is a constructive interference. So that is actually the constructive interference after the scattering events for the wave 1 and wave 2. If it again is following the same phase, we can say it is a constructive interference. So we can actually add the magnitude of both the waves to get a equivalent wave, which is shown as in the figure, okay, which is actually 2 times the magnitude of the amplitude of the initial waves. So this particular phenomenon is called as constructive interference. Now we are considering another set of waves. We again consider 2 waves. Previously, before the scattering or before the hindrance, we will be having 2 waves which are in phase. So after the scattering event, if we are seeing that there is a phase shift or there is a difference in the phase by an angle of 90 degree, or there is a phase shift by pi by 2, we can say now the 2 waves are having a nature which is having a phase difference among themselves. And if we are considering an equivalent waves, we can see these 2 waves getting cancelled each other. So when we are considering a net wave, it will be nullified, or there will be a neutral wave, or there will not be a wave. They can be getting cancelled each other. This particular phenomenon is called as destructive interference phenomena, which is taking place in the waves. So now when we are considering the diffraction phenomena, diffraction actually is a consequence of a specific phase relationship which is established between 2 or more waves which are scattered by different obstacles or different objects in its path. So if we are considering an X-ray beam, we will be having n number of such waves in these X-ray beams, so which will be traveling through the material, and it will be having different obstacles in its path, and after when it is striking this obstacle, it will be getting diffracted. So when these waves are getting diffracted or it is getting scattered, we can say that if it is following a constructive interference path, it can be called as a diffraction phenomenon. If the reflections or scattering from the hindrance of different beams or different waves when it is striking different obstacles, if these reflections or the scatterings are taking place in same phase as in the case of the previous case where before striking the obstacles, such relationships are called as diffraction phenomena. So the mandatory condition for diffraction phenomena to take place is it should be having a constructive interference. So diffraction occurs when a wave encounters a series of regularly spaced obstacles which are capable of scattering the wave and have equal spacing that which are comparable in magnitude to that of the wavelength of the incoming wave. So diffraction is a phenomena which is taking place in between series of waves when they are subjected to different hindrance or obstructions in their path. After their hindrance, or once they strikes this hindrance, they get scattered. If the scattered waves also follows the same path, they will have a constructive interference among themselves, which we will call it as diffraction phenomena. So this is very important when we are considering the X-ray diffraction techniques. For determining the crystallite structure, we should be having a incoming waves which is getting diffracted or which is getting scattered in a such a way that it is forming a constructive interference among themselves, or it is giving a diffraction phenomena. So the phase relationship between these scattered waves will depends upon the path length. Okay, this we already discussed. If they are following in same phase, still in the same phase, we can say they have a constructive interference. But if they are not following the same phase, or if they are out of the phase, we can say they have a destructive interference. Okay, or in such certain case they may be having a phase which is between the destructive interference and between the constructive interference. In such case we will call it as it will be having a partial interference. Okay, so a diffracted beam is the one which composed of a large number of scattered waves that have this mutual reinforcement among one another, which means so the diffracted beams is the beams which are having constructive interference. In another term, we can say the diffracted beams are the beams which have different waves which will be having the same phase as before it strikes the obstacle. So in XRD techniques or X-ray diffraction techniques, we will be using an X-ray, which is an electromagnetic radiation of high energy and shorter wavelength, for creating this diffraction from the material lattice or the atomic arrangements in the materials. So the wavelengths of X-rays are having an order of atomic spacing, which means the wavelength of the X-rays are very much comparable to the atomic spacing or the spacing between different atoms. That's why we are using this particular rays, which is the X-rays, for using for the characterization of the crystal structure in these particular techniques. So when a beam of X-ray, when it strikes a solid material, for example any particular material, any solid metallic material if you are considering, a portion of these beams will be scattered in all the direction by the electrons which are associated with the atoms. Okay, so which means we will be having different atoms periodically arranged in the material. So when these X-ray beams is penetrating or it strikes the atoms, these X-ray beams will be getting scattered by the electrons which is surrounding around the atoms. So the electrons around the atoms are actually causing the scattering phenomena of the incoming X-ray beams. Okay, so these X-rays will pass very easily through the interatomic spacing. It will not getting scattered or it will not getting hindered when it is passing through the interatomic spacing, which means the spacing between two atoms. So for example, if you are considering the figure, we can see a particular material and we are representing the different atoms between this particular material. When these X-rays are passing through the interatomic spacing, it will not get scattered. These waves, when it is passing through interatomic spacing, it can easily penetrate, but when it strikes an atom, it will get scattered or it will get deviated its path. Okay, so Bragg's law is one particular condition or one particular law which provides the necessary condition for diffraction of X-ray to take place among a periodic arrangement of atoms. So Bragg law actually provides the necessary condition for electron diffractions, okay, or the atomic diffraction. Okay, for example, if you are considering two incoming beam of X-rays, okay, or two incoming waves of X-ray, when we can see the first X-ray beam or the first X-ray wave, it strikes a particular atom at point P, then it is getting scattered through a particular path. Okay, so the actual path of that particular beam is 1P1 dash. Okay, now we are considering another incident beam which is 2, where the wave is having a particular path. When it starts from 2, then it strikes an atom which is positioned at Q, then again it is getting scattered and it moves in a path which is 2 dash. Okay, so the actual path which is traced by the second beam or the second wave is actually 2Q2 dash. So we have two particular waves of X-rays. These two X-rays, if we are considering, we can see the incoming beam of X-ray or incoming X-ray waves as well as the diffracted beam or diffracted X-ray waves, both are following same phase. So we can say a diffraction phenomenon has taken place. Okay, so how this diffraction phenomenon takes place, that is actually determined by the Bragg's law of electron diffraction or X-ray diffraction. Okay, so this is the schematic representation. We will be having two incoming waves, two outgoing waves, both are following the same phase. Then we are having different atoms. One particular layer of atoms actually represent one particular plane of atoms. So A actually represents, or A dash actually represents one plane of atoms. B dash actually represents second plane of atoms. So the distance between the plane A and plane B, it is represented by DHKL. Okay, this actually denotes the interplanar spacing, or we can also say it is the interatomic spacing between the atoms. So D actually represents the interatomic spacing or the distance between two atoms. So now we are saying for X-ray diffraction to take place, the Bragg's law must be satisfied. But already we know for X-ray diffraction or the diffraction phenomena to take place, constructive interference must be satisfied. So now we can say that the constructive interference of the scattered rays occurs if the path length difference between two waves is equal to whole number of the wavelength. Okay, I repeat, to constructive interference or the diffraction to take place between two scattered waves or scattered rays, the path length difference is actually a whole number times that of the wavelength, which is actually the expression for the Bragg law. It is the actual statement of the Bragg law. Okay, so it should be having a path length difference which is equal to whole number times the wavelength. So in another terms or in expression we can write it as n lambda is equal to d HKL sin theta plus d HKL sin theta. So now we will discuss how these values came. N lambda equal to 2 d HKL sin theta plus d HKL sin theta, which actually equals to 2d HKL sin theta. How this value has actually arrived. So we are going back to the previous figure in which we are considering the two beam path or two wave path. If we are considering the two wave path, we can say the actual quantity or actual amount of the path length difference. So actual amount of path length difference between these two wave, if we are considering, it is the extra distance traveled by the second beam or the second wave. Okay, if you are considering the two waves, the first wave is traveling a distance which is shorter when compared to the second wave. So second wave which is going and striking the second atoms or the Q atom, it is traveling an extra amount of distance. So this extra amount of distance is actual quantity of the path length difference between the two waves. Okay, that is clear. Okay, so the extra length of the atoms travel we have to determine. So for that we will be considering the symbol geometry. We will be we will be drawing two perpendicular, some connecting P and S and also P and T. So if you are dropping two perpendicular lines, we will get two included angles, okay, which is making between the angle between SPQ and also it is the angle between QPT, which are equal to theta each. So now we can consider the distance from 1 to P will be equal to the distance from 2 to S. Similarly, the distance from P to 1 dash will be equal to the distance from T to 2 dash, which means the extra distance which is traveled by the second wave, it is actually the sum of SQ plus QT, right? So the extra distance traveled by the wave 2 when compared to wave 1, it is actually SQ plus QT. This SQ we can determine as the particular value d sin theta or dHKL sin theta, because we have the PQ which is the interplanar distance, which already we know it is dHKL and the included angle is theta. So SQ actually it comes as d sin theta or dHKL sin theta. Similarly, if we are considering QT also, if we are considering that particular triangle, the included angle is theta and also we know PQ as dHKL. So the value for QT, the length of the QT will be equal to again dHKL sin theta. So actually in total the extra distance traveled by the wave 2, which is actually the path length difference, which is equal to SQ plus QT, which actually equal to d sin theta plus d sin theta, which is equal to 2d sin theta, or also we can call it as 2d HKL sin theta. Okay, so now we know the total value of that particular extra length of distance traveled. So by Bragg's law it is stated that this extra path length difference it should be equal to whole number of the wavelength. So if lambda is the wavelength of the particular wave, so whole number, if you are considering n as a whole number, it should be n times n. Thus the expression came as n lambda equal to 2d sin theta. This is actually the expression for the Bragg's law. So in order to have constructive interference, or we can say in order to have the diffraction phenomena to take place, the Bragg law must be satisfied, which means n lambda should be equal to 2d sin theta, where n is a whole number and lambda actually represents the wavelength, d actually represents, or d or dHKL actually represents the interplanar distance or interatomic distance, and theta is the angle of diffraction, okay, or the included angle of the diffraction. So n may be any integer, it can vary from value 1, 2, 3, etc. So that is the particular expression for the Bragg law. Okay, if Bragg law is not satisfied, then the interference will not be constructive, or it will be a destructive interference, and we can say the diffraction will not take place. So Bragg law, or n lambda equal to 2d sin theta, it is the necessary condition which should be satisfied so that we will get a constructive interference or diffraction pattern. Okay. Now we have another expression for determining the interplanar spacing, or the distance between the two planes among these particular crystal lattice. Okay, for each crystal system, this equation or the formula will be differing. For this is particular equation for finding for the simple cubic structure or the cubic systems. Normally we can say by using this expression we can calculate the interplanar distance for the cubic systems. So the magnitude of interplanar spacing, it is a function of the Miller indices, which is HK and L, as well as the lattice parameter. So A represents the lattice parameter, D, HKL actually represents the planar spacing, H, K and L represents the Miller indices. So if we know the Miller indices as well as the lattice parameter, we can find the interatomic spacing or interplanar spacing. In other ways, if we know the interatomic spacing and actually the lattice parameters, we can find the crystallite size, or we can find the lattice parameter of the particular crystal. Okay, so this is the expression for the interplanar spacing. dHKL is equal to a by root of h square plus k square plus l square, where d actually represents the interplanar spacing, a is the lattice parameter, h, k and l represents the Miller indices. Okay, so we told Bragg law must be satisfied for constructive interference to take place and diffraction to take place, but it is not the sufficient condition. It is the necessary condition for diffraction to take place. For diffraction to occur, there should be one more condition, which is actually regarding the type of crystal structure. For example, whether it is a simple cubic structure, or whether it is a BCC structure, whether it is an FCC structure. So for a simple cubic structure, this particular Bragg law itself is sufficient, because the atoms will be only arranged at the corners of the cube, and the diffraction phenomena exactly takes place as we have mentioned in the previous example, like as in the case of the particular condition which we have determined using the atomic arrangement as in the figure. But in the case of body-centered cubic, the condition is little different. In the case of body-centered, we have all the corners occupied by the atoms. Also we have another atoms which is positioned at the body center. So there may be diffraction from another particular side. For example, the beam which is coming inside the material, it have more number of scattering centers. So there will be scattering from the atoms present at the body center. Similar in the case of face-centered cubic structure, we have atoms in the face centers. So we will be having multiple scattering centers. So Bragg law should be satisfied. At the same times, there is another condition which is again the crystal structure dependent. For example, if you are considering the BCC material, one important condition is Bragg law must be satisfied. Also, we should be having the H plus K plus L value, which is the sum of the Miller indices value, must be even for diffraction to occur. Okay, so for the base-centered cubic structure, Bragg law must be satisfied. That is one condition, which is the necessary condition, and H plus K plus L must be even. That is the sufficient condition. Okay. For the face-centered cubic structure, similarly Bragg law must be satisfied, which is the primary condition or the necessary condition, and H, K and L must be either odd or even, which is the sufficient condition. So these are the different conditions which must be satisfied for the diffraction to take place. The primary condition is the Bragg law must be satisfied, then the material dependent condition for simple cubic, body-centered cubic as well as face-centered cubic structures. Okay. So next we will discuss about the actual experimental technique for determining this characterization of material using X-ray diffractometer technique. So the apparatus which is used, it is called as diffractometer, or also called as X-ray diffractometer. So the schematic representation is shown in the figure. You can see we will be having a diffractometer where we will be having a scale for measuring the angle of diffraction. Okay, then we will be having a source which is actually the region from which these X-rays are getting emitted. So source actually represents the origin of the X-ray beam. Then we will be having a position for holding the specimen, which is represented by S in the figure. So this position of S, the specimen, can be actually tilted about, or it can be rotated about a particular angle depending upon our requirement. Then we will be having a detector from where we will get the diffracted beams, or we will be collecting the diffracted beams which are incorporated with the counters and collimators. Okay, so the detector actually, it is positioned at a particular angle where it can collect the diffracted beam. So counter which is mounted over a particular carriage is used to find the angular position, and from there we will be having a collimator. This collimator's purpose is to get a well-defined beam path, to get a well-focused beam. Then we will be having a filter which provide a near monochromatic beams. So we have a source, we have a specimen, we have a detector, which are the important parts of a X-ray diffractometer. Then when we are doing this diffraction, or when we are passing an X-ray beam and then we are moving this specimen, or when we are moving it about a particular angles, we can see, depending upon the reflections of atoms or the scattering of atoms from the material, we will be getting the peaks, or we will be getting the diffractions at particular angles, okay, which will be recorded, or which will be collected inside the detector. So if you are considering a polycrystalline material, so we know the feature of a polycrystalline material. It will be composed of different grains, and inside any particular grains we can see the atoms will be arranged in a particular orderly fashion. So it will be having similar reflections from when we are considering inside a plane. And if you are moving from one grain to another grain, we can see the orientation of the atoms will be changing when we are moving from one grain to another. That's why we will be calling it as a polycrystalline material. So when we are considering the second grain, in that particular grain also the atoms will be very orderly arranged, but the order of arrangement or the angle of arrangement, it will be different. It will be in a different planes. So in the case of diffractometer, when we are rotating the specimen, we can obtain reflection from different planes, which actually corresponds to different Miller indices value, or it corresponds to different reflections from different planes. Okay. Then another important feature regarding the diffractometer is we will be having the incident beam at a particular angle, and the diffracted beam or the collected beam which is collected from the counter, it will be having a angle which is 2 theta value, which is 2 times the actual value, which means if you are rotating the specimen by an angle of theta, in net effect the counter will be rotated 2 theta times. Okay, this 2 theta value is called as the diffraction angle, or the angle which we obtain after the diffraction. So diffraction angle, by which we means it is an angle obtained at the collector range, which is 2 theta, okay, which is 2 times when we are rotating the specimen. So this is the actual representation of the actual X-ray diffractometer, which with all the connections which is placed inside a laboratory. So we actually make 2 measurements when we are doing this X-ray diffractometer. One is the angle of diffraction beam or the diffracted beam. Second one, it is the intensity of the diffracted beam. So we know, as we already discussed, when the counter is made to when the specimen is made to rotate at an angle of theta, the counter is actually making a rotation at an angle of 2 theta. This 2 theta is the diffraction angle. So we will be having a diffraction angle or the 2 theta value, and another one we will be having the intensity of the diffracted beam. So this intensity of the diffracted beams will increase as we are getting much more or multiple diffractions from the same planes. Okay. Okay, so if we are giving, as the number of constructive interference is getting increased, this intensity of the diffracted beam will get also enhanced or increased. Okay, so the figure actually shows a diffraction pattern of a powdered specimen of lead. In this we can see we will be having over the y-axis the intensity, and over the x-axis we will be having the diffraction angle, which is the 2 theta angle. Okay, and when we are considering, we can see a wave which is having different intensity and which actually shows the different planes. For example, if we consider the plane 111, which is the high intensity plane, we can see it will be having the maximum diffraction, and when we are going down, we can see there are very small planes where we will be having a minimum intensity. So as the intensity increases, the diffraction also getting increased. So that is how we get a particular pattern or the X-ray pattern out of the X-ray diffractometer. So when we are giving the samples for doing this XRD analysis or X-ray diffraction analysis, what we finally obtain is actually these intensity values and actually the 2 theta values. So we get the different planes, and also we know the different diffraction angles from which we can determine the crystal structure of the material. We can find the crystallite size of the material and also the different included angles in the material. Okay, and the different phases present in the material. So all these things can be analyzed using a X-ray diffraction patterns. Okay. So till now we have discussed how to determine a crystallite structure using a X-ray diffraction techniques, and how these diffractometer works, the constructive interference and the diffraction phenomena, the Bragg law, etc. Now in short we will discuss how to determine the crystallite size or the grain size of a particular material using the X-ray diffraction techniques. So this grain size measurement or the crystallite size measurement using X-ray, it is based upon a particular law or a particular equation which is called as Scherrer equation. So the actual representative of the equation, which is tau is equal to k lambda by beta cos theta, which is the different terms associated with this particular equation, where tau actually it means the size of the grain, okay, or size of the crystallite, okay, crystallite domain. So size of one grain means that one grain or one particular crystallite in which the atoms are having a particular orderly arrangement. So that is one particular grain. So tau represents the grain size. K actually it is a dimensionless shape factor, okay, which is closer to unity, which is having a it is a constant value which is normally considered as 0.94 or 0.9, okay, and lambda actually it represents the wavelength of the X-ray, okay, and beta it actually is called as full width half maxima, okay, which is actually a value which we obtain from the particular peak inside the X-ray diffraction pattern, okay. Theta is actually the Bragg angle, which actually is the half the angle of the diffraction angle, okay. So diffraction angle is the 2 theta, we will get half of that, we will get the Bragg angle. If we are substituting these values, we can get the value for the grain size. So previously I have discussed how to determine the interplanar spacing using X-ray diffraction techniques. Now we have determined how to measure the crystallite size or the grain size using X-ray diffractometer technique, okay. And finally we will be discussing the various applications of the X-ray diffractometer. One foremost application to determine the crystallite size. We can also determine the crystallite size which consists of a unknown material. So for known material we can find the crystalline structure. For unknown material we can find the crystalline structure of the material or the crystal structure of the material. To determine the crystallite size or the grain size of the material by using Scherrer formula, as we already discussed, and to determine different phases present in the material. If the material consists of if it consists of different multiple phases, or it is not a single phase material, so we can analyze that also using the X-ray diffraction techniques to find whether a material is crystalline or not, or also we can say it as to analyze the degree of crystallinity of the material. So the diffraction pattern will be different for the amorphous material when we are comparing the crystalline material. So we can also use XRD analysis for finding the degree of crystallinity of the material, okay. To find the phase fractions, if you are having a multiple phases, to find the quantification or the quantity of these particular phases from the XRD analysis. So these are the various applications of the XRD techniques, okay. Thank you.